Okay, go ahead. Okay, which number do you want me to do? 4?
Yeah.
Okay. Oh, okay. All right. Uh, we want to do the integral of cosine to the fifth.
I can't see your screen, by the way.
Oh, shoot. Sorry. I forgot to share it. Hold on. Okay. Can you see it?
Yeah, I can see it.
Okay. So I'll just use theta just cause. What I would do here first is I would probably make that 1 minus sine squared theta cosine cube theta d theta. And then I would distribute it out. So now I get and there's a few ways we could do this actually. Actually no. Yeah, I would just do it let's do this by parts. That's probably the best way to do this. So let's do sine theta times sine theta cosine cube theta d theta. And then let's make that dv. Let's make that u. And then we get u is equal to sine theta, du is equal to sine or du is equal to cosine theta d theta. dv is equal to sine theta cosine cube theta d theta. V is equal to uh this is u cubed negative, so negative, so we need a negative cosine to the fourth theta over 4 plus c, but we don't care about that. And then okay, so now what I would do is so now it's uv negative sine theta cosine to the fourth theta over 4 minus v du. So now it's 1/4 sorry, I'm gonna zoom out a little bit. 1/4 cosine. Am I tripping? Hold on. 1/4, yeah, cosine to the fourth theta, and that should be a plus because double negative. Cosine to the fourth theta times sine theta d theta. Does that make sense so far?
Wait, shouldn't it be cosine to the fifth theta d theta?
Oh, shoot. Yeah, it should. Whoops. And so, yeah, so cosine to the fifth, and then after that, so then we could set, and then how do we integrate this? Well, we would do, what would be the best way to do that? Let's just do 1 minus sine squared theta cosine theta. And then so that's cosine theta minus uh, sine squared theta cosine theta. Makes sense? And then that becomes sine cube theta over 3 sine theta. Okay, so we have everything, but we have this over here, right? How do you think we could eliminate that?
Subtract it to both sides because it's
Yeah,
all equal to.
yeah, so this is all equal to cosine to the fifth theta d theta. And then you know where to go from there, right? Do I need to do the rest? Do I need to write it
Oh,
all
I got
out?
it. I got it.
Okay, cool. All right. What other questions do you guys have? That's there's probably multiple ways to do that. Uh I feel like that's the easiest. Actually, you know what would be easier? You could do 1 minus sine squared theta squared cosine theta d theta, and then expand this out. So now you get 1 minus 2 sine 2 sine squared theta plus sine to the 4th theta. And then you see where I'm going with this?
Yeah.
And then distribute that to each of the terms and integrate separately. That's probably the easier way to do it, honestly. All right. Any other questions?
Yeah, number 6.
Okay, cool. Oh, okay. This one's. I feel like, shoot. Weren't we doing this one with Ashish or something, or was that a different one? Never mind. I might be thinking of a different one. Anyways, 0 e to the x over e to the 2x plus 1 dx. Well, oh, this is. I think the easiest way to do this would be a triangle. So let's just do a triangle. 1 e to the x, and that's square root e to the 2x plus 1. That's theta. Is that all you needed, or do you want me to keep going?
You keep going.
Okay. Let's do. So. Okay. So the interesting thing about this, right? So usually with triangle problems, we find the dx separately, right? But
Yeah.
e to the x, the derivative that's e to the x, so we can never get just dx. But the good thing about that is we can get both of these at the same time. So cosine theta is equal to e to the x. So then sine theta, negative sine theta, d theta is equal to e to the x dx. Okay, so now all we need is the bottom, which is it sine? Yeah, so sine theta is 1 over square root e to the 2x plus 1. Square both sides. Sine squared theta is equal to 1 over e to the 2x plus 1. And then, so now I'm going to ignore the bounds. I'll turn it back into terms of x. Or do you want me to change variables? I could do that too.
Yeah, could you?
Okay, change variables. So let me write this out first. Okay, so actually, I won't write it out. So we know that x is equal to ln cosine x. Is there an absolute value there? X can be negative. So yeah, okay, so we know this relationship, right? So if this is x is equal to 0, and this is x is equal to 1, and we want it to make in terms of theta, oops, that's a theta. Whoops. Theta is equal to cosine x, right? So ln cosine. Wait, am I tripping? Ln cosine theta. Whoops. Okay, so I did it backwards. Hold on. That is not correct. It is theta is equal to cosine inverse e to the x. So we found a relationship between theta and x, right? So now if x is equal to 0 in this expression, theta is equal to cosine inverse 1, which is what angle gives you cosine 1? 0. Okay, so theta stays 0. 1, e, okay, yeah, so our upper bound would be cosine inverse e. That's a bit ugly, but we could still do it. It probably works out in the end. So this becomes negative sine cube theta. Okay, so does that make sense?
Yeah, I got it.
Okay, do you need me to keep going, or I can keep going?
No, this is good. It's good.
Okay, yeah. Did you do you know if this, like, if it stays like that, or if it, like, comes out neatly at the end?
I feel like you can just do U sub.
Yeah, that's it. Try, dude.
Wait,
I just didn't get why.
how'd you
E
do
to the
U
X.
sub?
Yeah, U goes E
Oh
to
yeah,
that.
U over.
That'd
right?
be 1 over.
Oh wait, no, 1 over e squared. That's still a
Yeah.
triangle problem though, right?
Yeah, but that's a way simpler triangle problem.
Oh yeah, it is.
Oh wait, and then you triangle from there, right?
Yeah.
Yeah, triangle.
U
from there.
one. Oh yeah.
Yeah.
What problem is this?
Number 4 or number 6 on whatever he said.
HD.
Let's see. Thank you.
I feel like the setup is you still have to go through this. I mean, we know that this is tangent, but like if you were to do it out by hand, you would still have to go through the same stuff, right? Or am I? Oh no, wait, you would just do sine squared. So yeah, that is simpler. Right? Hold on. Let me do this out a little bit more. And then cosine squared theta. Yeah, that is easier for sure. So yeah, I guess if you do a little bit of like, and then we know how to change the bounds, right? So, or do you need me to change the bounds on that?
No, I got it.
All right, yeah. So
Wait,
I guess
page E or page E?
was that asked towards me? Because I don't know what page it is. It's just.
Oh no, it's I don't know. Whoever sent it, was it Derek
Oh,
or
yeah, it's page D.
page D?
Yeah.
All right. Is there anything else?
Can we go over some hyperbolics?
Sure.
I can send a page. I was actually absent on the day he taught hyperbolics, so
Okay.
I don't know what they are.
Okay. Cool. I can explain them. So, hyperbolics. I'm trying to find the best way to explain it. Yeah. So, hyperbolics are. Sorry, I'm just trying to think. There's a lot of different definitions for hyperbolic. I'm just trying to think. Yeah. Okay. I guess the easiest way to define hyperbolics are two functions. Actually, I haven't thought about it. Sorry, give me 1 second. I want to see if there's because I know what they are, but uh. uh okay, they come up in a lot of places, but okay, give me 1 second. Actually, I'm going to. I do have it written down somewhere. Okay, I found it, but it's not as good as I thought it would be. So, I mean, yeah, I guess I don't really have a definition for these. I'm gonna be honest, but
Okay.
so since x is equal to e to the x minus e to the negative x over 2, and cosh x is equal to e to the x plus e to the negative x over 2. And the whole relationship between them is that this squared minus this squared. Unlike sine and cosine, where sine squared plus cosine squared is equal to 1. Or is it 1? Yeah, it is. Whoops.
Yeah.
Yeah.
It
So,
is.
anyways, so unlike that, this squared minus this squared is equal to 1. There's some relationship. I'll have to go look at it, a little more, and then I'll send it in the Discord. But
Alright.
yeah, so that's that, right? But anyways, these are the definitions. I'll see where they come from, and I'll send them in the Discord if I find them. But if you notice, sinh x, the derivative is equal to cos x, and same the other way around.
So there's no negatives?
No, because if you take the derivative, these are the definitions, right? So if you take the derivative of this, right, e to the x
Mm-hmm.
minus, let me just do it out. E to the x minus e to the negative x times -1 over 2, right? That's the derivative. And then the negatives cancel out, so that becomes a positive. And then that's cos x. So,
Got it.
yeah. I'll look for, I don't know, I'll have to go look at it and see if there's a more satisfying explanation. But for now, just, yeah, those are two functions, and they show up a lot. Okay, so do you have a specific, that's pretty much all that there is for hyperbolic. So if you have a specific question, I could do that.
I mean, I just sent the two hyperbolic pages that he had in the packet. So there's one that's just integrals of x cos x with bounds of 1 and 0.
Okay. And okay, do you just want to do number 1? I can do number 1.
Yeah, just so I could like see how it works.
Okay, x cos x dx from 0 to 1. Okay. Well, I mean, this works pretty similar to just x cos, like how you would integrate x cosine x. And that's not to say that there's some special, there might be, I don't know, but I don't want to say that there's some special connection between cos and cos right now, because I'm not 100% sure about that. But you would integrate them pretty similarly, because their derivatives repeat, kind of like trig functions derivatives repeat. So anyways, I would do this by parts.
Mm-hmm.
So u is equal to x, du is equal to dx, dv is equal to cos x dx, v is equal to sinh x. So it's uv x sinh x minus v du. So sinh x dx, and then that's cos x. So that's plus c. That's it. Oh, and then you evaluate the bounds too. Let me do that.
Got it.
So 1. So we know that sinh is e to the x minus e to the negative x over 2. Cos is e to the x plus e to the negative x over 2. All right, let's plug in 1. We get 1 times sinh 1. Sinh 1 is e to the 1 minus e to the negative 1 over 2. Okay, so let's put that e minus 1 over e over 2 minus cos. Cos 1 is e plus 1 over e over 2. And subtract that with 0, sinh 0, that's 0. So 0 minus cos 0 is 1 plus 1 over 2, which is 1. And then this here, that's equal to e minus 1 over e minus 1 over e over 2. Those cancel. That's negative 2 over e over 2. So that's negative 2 over 2e, which is equal to negative 1 over e. Minus, oops, I forgot. Bring that all the way over here. I forgot about this. Plus 1. That should be the answer.
Got it. Thank you.
Okay. Is there any other questions? That's how all of them go, really. So hyperbolics are not that hard.
Got it.
And then
Are these
actually,
used often?
oh, what were you saying?
Are these used often, like in BC?
Yeah.
Or not as much?
Yeah. So, I can't really, the derivation's kind of a lot. But basically, they show up here I actually have the derivation for the specific one. That was what I was looking for. They show up. Hold on.
Wait,
It's not.
what does it mean by like when asked to put in like terms of coach and cinch?
So yeah, actually, I was about to say I jumped the gun a little bit. You don't need to actually put it in terms of E. Just put cinch 1 minus cosh 1 minus. So this is basically what he wants you to do. Instead of actually evaluating them, you just put that. And then he does want you to know that cosh 0 is what again? 1. So he does want you to know that. And then cinch 1 is 0, I think. Right? E to the x minus cinch. So the only two things you need to evaluate are cinch 0 is equal to 0 and cosh 0 is equal to 1. Those are the only two things you need to evaluate. But everything else just leave in terms of cinch and cosh. That's what he says. Does that make sense?
Yeah,
Okay.
that makes sense.
All right. So is it possible you guys can integrate that, right? Or am I?
Yeah.
Yeah, it's just 1 plus c
Oh, and
squared to
then
the power of
yeah,
1
yeah.
half.
And then that's once you do it out, I won't do it out right here, but it's that, right? And then that is cinch inverse x. Yeah, actually, no, this doesn't even tell me what cinch means either, so I don't know. I'll have to look at what cinch is useful. It shows up in catenaries, which is basically when you hold two ends of a rope, the curve it makes. It shows up there because obviously it makes a hyperbolic. Well, once you prove it, it makes a hyperbolic shape, which makes kind of sense, right? This is a hyperbola, so you can imagine someone holding two ends of a rope. So I don't know. I'd have to look. I should look into what they mean, but for now, just take it at face value for now. Any other questions?
13 in the picture that I sent.
13 or I didn't hear that.
Yeah, 13.
Okay. 13. Okay, let's do that. So 1 over x squared minus 4 to the 3 over 2. Okay. I think the best way, actually we could leave this 3 over 2 alone. I think that would make the most sense. So what I would do is I would create a triangle, because this is kind of intimidating, but honestly, you'll see why it isn't in a second. So x2 square root x squared minus 4, right? Tangent theta. Tangent theta is equal to 2 over square root x squared minus 4. So 1 half tangent theta is equal to 1 over square root x squared minus 4. Okay, so that's one piece of our puzzle. Now we need a, oh, and then, whoops, actually that isn't done yet. So we want a 3 over 2 in our denominator, right? So what we want to do is raise both sides to the 3 over, well, it's already 1 over, it's already to the 1 half power. So we want to, so that's x squared minus 4, negative 1 half. Sorry, I'm being kind of slow for some reason. There we go. So raise it to the cube power, and that should work. So then tangent cube theta over 8 is equal to 1 over x squared minus 4, 3 over 2. Okay, that's one piece. And we need a dx. Is it secant? No, cosecant. Cosecant theta is equal to x over 2. So 2 cosecant theta is equal to x. 2 negative 2 cosecant theta cotangent theta is equal to dx, d theta. Okay, so that's that's one. That's our other piece of the puzzle. So then if we put this in terms of theta, we get, I'm going to put negative 1/4 on the outside, get rid of the constants. Tangent times cotangent is 1, so that eliminates 1. So we get tangent squared theta times cosecant theta d theta, right? There's one. Wait, hold on. I'm trying to think of the best way to do this. Yeah, okay. I guess the easiest way to do this, I wouldn't try doing it by parts. There's no reason to do so, really. Sine squared theta over cosine squared theta times 1 over sine theta. Boom. Sine theta, 1. So we get sine theta over cosine squared theta d theta, negative 1/4. Do you know where to go from there, or? Oops, that is.
Yeah, fine, thank you.
I don't know why I wrote cosh there. Should be centered. Okay, yeah. Okay, any other questions?
Also, is that just 1 over u du?
Not 1 over u du, because then you get ln, and you need a 2. If it was 1 over u du, your du would be 2 cosine theta negative sine theta, but it is u to the negative 2 du. Right? Because does that make sense why it's not 1 over u du? Because then your u is cosine squared theta and not cosine theta.
Right, that makes sense.
Okay. Any other questions? I see number 11 is circled on that thing you sent. Do you need to do that? And then, yeah, also with your questions, what do the hyperbolics really mean? I haven't thought about it in a while, so I kind of forgot. So I'll get back to you guys on that. I'll send it to you in Discord, an explanation. But for now, just know that the hyperbolics are very fancy functions you'll learn about more later. So, okay. Do you want me to do number 11? Because it is circled. Or is there other questions we can get to as well?
Oh yeah, that's fine. I got the number 11.
Okay. What else?
I don't know if the page J big top bargains, I don't know if that's different from the first Kosh sign one.
Okay, yeah. So, which one?
Just anyone.
Okay. Do you want to pick one we can start with? I already did cosine to the 5th, so let's not do that one. You can look back in the video once I post it if you want to see that one.
Got it. We can do secant to the power of 4 theta.
Okay. Let's do that. Okay. What number is that? 2. Okay. Secant to the 4th theta d theta. Well, sine squared plus cosine squared is equal to 1. Divide by cosine. We get tangent theta plus 1 is equal to secant squared theta. Yeah, so the easiest way to do this would be just to take out one of these. So tangent squared theta plus 1 secant squared theta d theta. And then we distribute and separate the integrals. So we get tangent squared theta secant squared theta d theta plus secant squared theta d theta. Okay, this one, pretty easy, tangent theta. This one, we could do, if I turn this into sine squared theta over cosine to the 4th theta, this probably doesn't work, but cosine squared theta over cosine to the 4th theta, yeah, because then if you split them apart now, you get secant to the 4th theta, and then you don't know how to integrate that all over again, so that does not work. You could. There's probably a way to do this by parts.
Do UDV, the secant data, and then secant data times tangent
Yeah,
data.
yeah, that's probably the best way to do it. Is this what you're saying?
Oh, you split secant squared theta, the secant data and
Yeah,
secant data.
I was thinking about that as well. I was wondering which way would.
Oh wait,
Yeah.
never mind. Sorry, you do a tangent. You split the
So-
tangent squared to tangent data times tangent data.
So then you get tangent theta times tangent theta times secant squared theta. Do you
Yeah.
do you split this too, or?
No, just leave it. And then
Oh,
you're
yeah, I see what you mean.
Yeah.
This is EV. And
Yeah.
this is U. Okay. Well, if U is equal to tangent theta, then du is equal to secant squared theta d theta, and then dv is equal to tangent theta secant squared theta d theta. B is equal to, let me zoom out here. Tangent theta secant squared theta d theta. That's u du. So let me actually just erase that. I can just write that. Tangent squared theta over 2. Okay. Okay, yeah. And then now we would do UV. So tangent cube theta over 2 minus v du tangent squared theta times secant squared theta. Oh yeah. Okay. So this would be minus 1/2 tangent squared theta secant squared theta d theta, right? And that seems like a bad thing at first, but we know that this is equal to tangent squared theta secant squared theta d theta. So we can just make this into an algebraic expression and then treat it like an algebra problem. So then once you isolate that onto that side and divide and all that, you get 3 over 2 on this side, so 2/3 times tangent cube theta over 2. I skipped a few steps there. Does that make sense?
Yeah, it makes
Okay.
sense.
So now it's tangent cube theta over 3. I'm gonna write it over here. Tangent cube theta over 3. And then we forgot about this, so let's put that over there. Plus tangent theta plus c. Is that right, or did I mess something up? Alright, I think it's good. We'll see. That should be good.
I don't know if Shai posted the answers or not. I don't think he did.
Yeah, I mean, if he doesn't post the answer, if he doesn't post the answer, that's you could just search it up as well at that point. Okay, for what trig functions would we use the half angle formulas to solve the higher power integrals? I only ever use the half angle formula when it is squared. Has he showed you how to do it for powers higher than 2? Because if it's powers higher than 2, usually I just split it up like we've been doing with trig identities and go from there. Has he shown you powers higher than 2? Or
Yeah.
We sine to the 4th, and that one has half angle, but the other ones don't.
okay, which one? Let's do it right now.
Also for the last question,
Uh-huh.
isn't it supposed to be multiplied by 2 over 3?
I think I already did that, right? Here, and then I added that over to this side, so that's 3 over 2 times the
Yep.
integral. And then yeah, so then I got this over here. That's where I multiply it by 2 over 3. Canceled out the 2's, got 3.
Oh, I see. That makes sense.
Because you don't do it over here, because we did this separately, right? These are
Yeah.
separate things that we figured out.
Uh-huh.
Does that make sense, or should I elaborate further on that?
Oh, that makes sense. You just multiply it to the tangent cubed because that's like separate.
Yeah, that's what we did. because we found this, and then all this work was just to find this side of the integral.
Mhm.
Okay, so what was the one where he showed you for a power higher than 2? Because I swear we've never done that. We usually just split them apart, but
Sine to the fourth power.
okay, let's see. Sine to the 4th theta d theta. So what's the problem with doing this? Did you try this? Because then you get sine squared theta d theta, and then you use half angle for that, minus sine squared theta cosine squared theta d theta, and then you would do sine theta times cosine squared theta d theta ev sine theta u. It should work. Hold up. I might just be going in circles, everything will cancel out later, but let's see. Let's hope not. Sine theta is u, and then du is equal to cosine theta d theta. dv is equal to sine theta cosine squared theta d theta. v is equal to cosine cubed theta over 3 with a negative, right? And then uv v du. Okay, I see where the problem occurs, because then we get cosine to the 4th theta, and then we're kind of back where we started. Yeah, I'm trying to think. Okay, well, actually that might not be a
Use
problem.
these parts again, I think.
Yeah, that might
Or
not
sine
be-
squared theta, cosine squared theta. Does that not work?
Wait, I could use parts like this, is that what you're saying? Or
So you keep doing the same
No,
thing
like you did
over.
before. Does that not work?
wait, hold on, sorry, I'm blanking a little bit. What did you guys say?
Just do parts like you did there.
Okay,
yeah.
so continue here and it should work.
Yeah,
is
yeah.
that what you're saying? Because then you get, because the main problem I'm getting here is uv negative sine theta cosine cubed theta over 3 minus v du, and now we get cosine to the 4th, I'll put a third out here, theta d theta, right? And then how do we do that? Because if I try doing this whole process, it's likely that everything is going to cancel out and get 0, right?
Yeah.
So I guess that's why you don't want to do this by parts. You want to do it with I think they call it power reducing. That's what they do it for. Yeah, okay. I mean, the only I guess for what trig the answer to your question for what trig functions would we use the half angle formulas? It's when if you try it by parts, you get this. And more specifically, that happens when it is sine or cosine to an even power, I think. Is that I think that's how I think that works. Does that make sense? Does that I can show you guys this. I'm gonna show you guys this with half angle just to confirm what I'm thinking. Does that make sense though?
Yeah, it does. Thank you.
Yeah, and I'll show you the reason for that, actually. Or I'll try and show the reason for that. Okay. So, sine to the 4th, theta d theta. Well, we know that cosine 2 theta is equal to 1 minus 2 sine squared theta. So then 1 minus cosine 2 theta is equal to, over 2 is equal to sine squared theta. So now what we do is we plug that in here and we get the integral of 1 minus cosine 2 theta over 2 squared d theta. So that's 1 minus 2 cosine 2 theta plus cosine squared 2 theta over 4 d theta. And then you guys know where to go from there, right? You can split these pretty easily, and then you can do another half angle with that one, right? And so should I do it out? I'm trying to think, because the reason you don't do it if it's sine to the 5th theta d theta is because you will have an extra sign out here, right? So you would have an extra sine theta d theta, and wait, you could, yeah, because then once you do that, then you have different thetas going on, and that is just more complicated, and I don't think it goes anywhere. Does that make sense why it's only even powers?
Yeah, that makes sense.
And I guess the reason you don't do it with tangent or cotangent is because our identities are in sine and cosine. It would just be more work to do it that way, I'm assuming. Does that make sense?
Oh yeah, that makes more sense. Thank you so much.
Okay. I mean, if you want to see it, I can try doing, yeah, I just don't see how you would do it with this. I guess you could divide by cosine theta, but then see again, you're mixing 2 theta and theta if I divide by cosine squared theta. So yeah, it's just only when it's sine and cosine to an even power. And then
What happens if you continue solving this?
okay, yeah, let me do that. So if you continue, let me split this up. So this would be 1/4 d theta minus 1/2 cosine 2 theta d theta. These we know how to do, right?
Yeah.
Okay, so I'm just gonna not do those because you can do those yourself. I'll just do the last one. Cosine squared 2 theta d theta. Ignore that was. So we know that cosine. Actually, I'm just trying to figure out. Yeah, okay, yeah. So cosine, let's call this. Trying to figure out the best way to do this because we can for simplicity's sake we can call a 2 theta, but then we need to find a dA, or would it be easier to just? Yeah, okay, let's just do it this way. Yeah, it's probably easier. Cosine 2 theta is equal to 1 minus 2 sine, or the other way. Oops, not that. Okay. 2 cosine squared theta minus 1. Let's multiply, since these functions, yeah, let's plug in 2 theta per theta, so then we get cosine 4 theta. Does it make sense what I said there? We basically plugging in 2 theta for theta and 2 theta for the theta over here, and everything should stay the same. That's the reason why we're able to manipulate the inner bounds of these functions. So, because we're basically just plugging in variables for it. Cosine 4 theta is equal to 2 cosine squared 2 theta minus 1, and then we isolate this because that's what we want. So then we get cosine 4 theta plus 1 over 2. And then do you see where it goes from there? Because then you can split them apart again. Or should I keep doing it?
Can you keep doing it?
Yeah, okay. So then I don't know how to move this. Yeah, okay, I won't bother. So, oops. So, 1/4, I'll leave that on the outside. Are you okay with me skipping some steps here? I'm just splitting them apart.
Yeah. You could skip some steps.
Okay. I'll actually factor out the 1/2 too as well. So let me erase that. So I'll put an 8 out here, and then from there this is theta plus my thing's getting in the way. Theta plus, what is that? Sine 1/4 sine 4 theta multiply 1/8, and then you know how to do those, right? Or
Yeah, I get those.
okay, so yeah, so then boom, you got your integral plus c. Okay, makes sense?
Yep, thank you.
Yeah, okay. Alright, anything else? I think you guys are mostly just doing review. I don't think do you guys learn any new integration techniques? You guys already kind of knew triangle and parts and all that last week, right? So
Yeah.
okay. Yeah. Is there any other questions? Or and does it make sense? Also, I just wanted to add, I'm gonna actually let me do this, because I did send something that even I wasn't thinking about until someone asked. So does anyone have any questions first before I talk about this? Or okay, I see someone sent something. Let me check. Okay, 3. All right. Yeah. Okay, this one I was showing to someone during lunch, I think a few days ago. I forget, but this one's pretty cool. So it goes back to the idea of using a triangle to manipulate functions, right? So this one, we want to prove, I'll just write it at the top, tangent inverse x. I like putting mine in front. I don't know. I just think it makes more sense. I don't know why we put them in the back, so I'm just going to do that. Let me put that. Be a tangent inverse 1 over x is equal to cotangent inverse x from b to a. Okay. So we want to prove that tangent inverse b minus tangent inverse a is equal to tangent inverse 1 over b minus tangent inverse 1 over a. And I'll just tackle this for now. I'll get to that later. So let's make a triangle for each of these values, right? So this is theta 1 and this is theta 2. Let's say that, right? For now, for the sake of simplicity though, I'm just going to use theta for both of them. Should I actually? Or should I use different variables? Yeah, fine, I'll use different variables. Okay, theta 1, right? That's the angle we get when we plug in b into the tangent inverse function, right? So b over 1 is equal to theta 1. And then this side is square root 1 plus b squared. Let's do it over here too. Theta 2. Hold on. Actually, sorry about that. I'm going to make these bigger just because I'm going to have to write more in them. Theta 1, b 1. I'm just going to put dot 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 here because we don't need it. A1 theta 2. Okay, so if that's theta 1 and this is a right triangle, the other angle is pi over 2 minus theta 1, right? And this one is pi over 2 minus theta 2. Does that make sense? Okay, so tangent inverse b we can say is the same as b over 1, right? We get this angle. That's the same as sorry, my brain's shutting down here first. I don't know why. That's the same as, hold up. Okay, yeah, it's the same as tangent inverse pi over 2. Hold up, I don't even know what I'm doing right now. That's, so this is equal to theta 1. Sorry, I swear I know how to do this. I'm just okay, so yeah. Okay, I need to look at this side so I know what I'm doing. So what we want tangent inverse 1 over b, right? Well, this is equal to we want to get theta 1 out of our tangent inverse function. So we will get that if, shoot, what am I even doing right now?
Oh, you said you set the other angle. Set it equal to the other angle. So it's 90 minus theta 2. Or 90 minus tangent negative 1 over b.
Oh, yeah. Oh, shoot. Yeah. Hold. Okay, yeah. So, yeah, okay. Let's. Dang, there's a lot of. Yeah. So this is. So if this is theta 1, and this is. Shoot, I already used theta 2. Okay, let's call this theta 1, right? And then this is pi over 2 minus theta 1, right? Tangent inverse b is equal to pi over 2 minus theta over 1. Right? And then minus. Okay, yeah, now we're getting somewhere. Okay, I don't know why I was blanking there for a second. Ugh. Okay. Does it make sense? Sorry, that was a bit messed up, but does that make sense what I did so far? So this is pi over 2 minus theta over 1 minus pi over 2 minus theta over 2. Does that make sense?
Yeah, that makes
Okay.
sense.
So then if we distribute this out and then add, we get these two cancel out and we get pi over 2 minus pi over, theta over 2 minus theta over 1. So theta over 2 is equal to, we can say, tangent inverse 1 over a, right? Oh, there's a negative here. That's why I was, there's a negative here. So tangent inverse, okay, this is getting, I don't know why I can't just move mine. All right, tangent inverse 1 over a minus tangent inverse 1 over b. Does that make sense? How I got that? Or
Wait, sorry, I joined a little late. Where did you get pi over 2 from?
so if this, in this right triangle, if I call this angle theta 1, we can agree
Yeah.
that this is 90 minus theta 1, right?
Right, okay, yeah. Okay,
And
okay,
so,
yeah, I see it.
yeah, and so in this triangle I made, this is the angle you get from this, right?
Yeah,
This tangent inverse opposite over
Yeah.
hypotenuse. So
okay,
yeah, so that's where I got the pi over 2 minus theta over 1.
alright, thank you.
Okay, yeah. So yeah, so that's that, right? And then, but you're probably thinking, well, that's not this, right? Well, it is. It's the negative of that, right? So that's where the negative comes from. Does that make sense? I feel like there was a way I did it without so many variables, but does that make sense how I got that?
Yeah.
Okay. I feel like, damn, I felt like there was, I swear, I did it like without so much stuff. Tangent inverse b is equal to that. Okay, yeah. Yeah, I guess that's, I don't know, tangent inverse b, I call that theta 1. Yeah, okay, I guess you can do kind of the reverse as well. Should I bother doing it that way? Do you guys want to see another, like it's very similar. It's just slightly different. I'll go ahead and show it. So instead of having so many variables, the way I used to do it is, okay, I guess I'll just have to. So I still, now instead of having, so that's theta 1, right? And then this is b1, dot dot dot, and then this is theta 2 a1 dot dot dot. So this is equal to theta 1 minus theta 2, right? And then that's equal to okay, theta 1 minus theta 2, and that's equal to pi over 2 minus theta 1. Shoot. Sorry, I don't know why I'm messing up so much today. So
I think someone's
pi.
mic is unmuted.
Oh, are they? Oh yeah. Okay, I'll mute that person for now, unless they have a question. So I can like. Okay, there we go. Okay. Dang, I'm so tired today. I don't know why. Okay, pi over 1. That's equal to negative. So that's pi over 1 minus pi over 2 plus pi over 2. Okay, there we go. Sorry. I don't know. So minus. Can we agree on that? Does that make sense? I just added pi over 2 and subtracted to each of them. Right?
Why are you adding pi over 2 and subtracting pi over 2?
You will see in 1 second. Because what I'm going to do is I'm going to say negative. Negative. This Zoom sucks. Okay. I'm going to write it off to the side. Is that okay? Because I have a lot of space on the side. I don't
Yeah,
know
that
why.
works.
Okay. So I'm going to write it here. I'm going to say negative. Okay. Negative plus pi over 2 minus or plus, yeah, plus. That's what I got. I'm kind of squishing it, but does that make sense? How I manipulated it to get that? Does that make sense? Sorry. I can explain it a little bit further if. So all I did basically was I wanted this angle. I wanted to make everything in terms of these angles, which is pi over 2 minus, right? So I put in some, and then I just I manipulated it so I could get these. Does that make sense? Okay.
It kind of makes sense, but I think the other way was more intuitive.
Okay, if it is, then cool. I like this way just because it uses less variables, and then I can be like, okay, well, that is equal to tangent inverse 1 over b, and then that one is equal to, and then these cancel out, so then that's plus, there's a minus out here, and then you see where it goes from there. So yeah, that was probably actually less intuitive now I'm thinking about it, but that's the way I like to do it, just because now I don't have, yeah, I don't know. Anyways, okay. Okay, now let's do that last one. The last one's way easier, so let's okay. Do you want to I'm gonna prove these, right? Because if at worst, right? I bet you guys now that I've showed you, you could probably figure this out, right? But for now, I'm just gonna show this because at worst you could prove this and improve that if you like somehow forget or something. So, all right. Okay. Anyways, yeah, I don't know. Come on. Is there a way to like move this? Oh, there is. Okay, cool. Let's go. All right. All right. Okay. Sorry for being for taking things slow. Actually, you know what? I'm gonna prove this and this, if that's fine. So tangent inverse b minus tangent inverse a. Okay, so theta 1, B1, theta 2, A2, or A1. Okay, and then dot, right angle, right angle. Okay, so that is equal to cotangent. So tangent inverse B, right, is equal to cotangent inverse. All right, hold up. Am I blanking? I don't know why I'm blanking right now. So it's also equal to cotangent inverse B over 1, or 1 over B. Is that the way I want to do it? No, actually, I'll just do it this way. That's 90, or not 90, pi over 2. Okay, yeah, this is where it is. Okay, pi over 2 minus this angle, right? Theta 1 is equal to pi over 2 minus that angle. Does that make sense?
Yeah.
Okay, so then, okay, yeah, I don't know why it took me so long to register this, but then now it's pi over 2 minus, let's say, cotangent inverse B over 1, or B, not B over 1, B, right? Okay, so yeah, okay, so this wasn't that bad. I don't know why I was taking so long. So basically, this is the same strategy you use, where you put it in terms of the other variables. The only thing that changes, whether you want to go from here to here or here to here, is instead of saying this, I could have also said tangent inverse 1 over B, right? Does that make sense? That's probably a lot simpler, I think, than how I was trying to explain as two separate things. It's actually the same exact proof. It's just what changes is what I say this is. Should I keep going, or does that make sense?
That makes sense.
Okay. Yeah, I don't know why it took so long there. Okay. Does that make sense? Does anyone need me to do it? I can do it fully now, real quickly, but I don't know. Others, you guys might have more problems that you want me to do. So, and it's a similar thing for you guys know how to do 4 and 5. It should be very similar. So, oh, okay. Why does that not work? Okay, let's do it the way you're doing it. So you wanna do x tangent inverse x dx, right? Okay. And you made u tangent x du. Wait, Hunter, what did you do here? You made u tangent inverse x. Did you do a triangle? Sorry,
Yeah, I did parts, and then the second half of the integral, I did trig sub.
Okay, so you did parts and you made your u tangent inverse x, right?
Yeah.
Okay. Let's do it let's do it switched first, because that's the easier way. I don't know if you realize that and you're just doing it a harder way. I can do it this way. I'm gonna do it this way, but I just want to show you the easier way first. And that is
Okay.
to make this u is equal to x. U is equal to x, du is equal to dx, dv is equal to tangent inverse x, v is equal to tangent inverse x, there's a dx here, dx, right? And then, okay, let's do that separately. U, that's how you do it. Whoops, that is not how you do it. dv, u is equal to tangent inverse x, du is equal to, I'll spare the triangle for now. I think it's this, right? dv is equal to dx, v is equal to x. So now it's uv tangent inverse x plus, or not plus, times x minus b du, which is x over x squared plus 1. And then you would do 1 over u du, right?
Yeah.
So then you put a 2 and then a 1 over 2. and then you get ln x squared plus 1 1/2 minus x tangent inverse x. Is this easier or am I? Yeah, this is not easier, is it?
I don't think so.
Yeah, okay, I don't know what I was thinking. Yeah, that is not easier. Hold on. Okay, let's do it your way. Your way is probably correct then. If that, because I was thinking that would be easier, because then we would get rid of the inverse trig, but then we just get a bunch of other stuff. So tangent inverse x times x dx. So this is what you did, or am I?
Yeah.
Okay, so du is equal to 1 over x squared plus 1. dp is equal to x dx. b is equal to x squared over 2. Okay. So uv x squared over 2 x squared over 2 times tangent inverse x. There it is. And then x squared over 2 tangent inverse x. Oops, sorry, I'm blanking right now. Minus, there it is. Okay, minus v du x squared over 2 times x squared plus 1.
Mhm.
That's right. I'll put the 1f out here just for simplicity's sake. Okay. Then what do we want to do? U plus 1 over u. No, let's just do a triangle. That's probably easier. So let's do a triangle. I'm assuming that's what you did.
Yeah.
Okay. X1 square root x squared plus 1. Theta. Okay. Tangent squared theta is equal to x squared. So that's one part of our puzzle. 1 cosine squared theta is equal to 1 over x squared plus 1. It's another piece of our puzzle. And then we need a dx. Tangent theta. Secant squared theta d theta is equal to dx. Okay, that's
For the x squared over x squared plus 1, I just made that sine squared theta.
Wait, for x squared over x squared. Oh yeah. And that should work because these will.
Yeah.
Hold on. Yeah, that should work. Is there a reason? So you made that. So instead you said sine squared theta is equal to x squared over x squared plus 1, and then you need a dx, which is, yeah, that works because that's just tangent squared theta, because these will cancel out once I put them out together, right? So yeah, that totally works. I'll just keep doing it my initial setup because it comes out to the same thing right after anyways.
Yeah.
So I'm gonna do it off to the side here just so I have more space. So that becomes tangent squared theta times cosine squared theta times secant squared theta d theta. Those cancel, so it's tangent squared theta d theta. Okay. What's the best way to do this? We could do. Yeah, let's just do 1 plus tangent squared theta is equal to secant squared theta, right? So this is just secant squared theta minus 1 d theta. So that's tangent theta minus theta, right?
Yeah.
And then we need to turn that back into terms of x. So tangent theta is x minus, let's just do tangent inverse x. I think that's
Oh.
it, right?
Wait, yeah. I see.
Did you put it in terms of x back into terms of x, or?
No, I accidentally left in terms of theta, and I randomly just switched it to x.
Yeah. Okay, I suspected that because I was about to do that too. What's an easy way to avoid that? Well, if you remember that, yeah, I guess you just, yeah, I guess that was just a silly mistake. Because you gotta remember that this is in terms, we made this in terms of theta, so you have to always turn it back into terms of x once you're finished with it.
Yeah.
Yeah, I guess that's, yeah. All right. Do you need me to keep going, or?
No, I'm fine with that.
All right. Okay. Any other questions?
Can you go over the monotonic functions?
Monotonic functions? Okay. You're gonna have to remind me what those are. Do you have like problems or something for it?
Yeah, I sent a picture.
Okay, let me check it out. Let me clean this first.
I think he said if it's monotonic when it like always goes up or always goes down. It can't have both at once.
So always increasing, always decreasing? Is
Yeah.
that what you're saying? So that would just be when the derivative is always positive or negative, right?
Yeah.
Okay. Where'd you send the problems? trying to find them.
I'm sending them right now.
Oh, okay. Yeah. All right, hold up. Let me go get water real quick while that's sending.
Yeah.
All right. Did you send it? I think
Send
you
it
did.
in.
Yeah. Okay.
Indeed.
I see it. And therefore has an inverse. Oh, okay. So the reason that only monotonic functions have an inverse, does someone want to tell me why?
Because only one y has one x.
Yeah. Because if you think about it, how do we tell if something's a function, right? We do the vertical line test, which is essentially for every x, there's only one y, right? And all an inverse does, instead of having x and y, we flip it. So now this is x and this is y, right? That's all we're flipping. So now our vertical line test becomes this, right? And so now for every x, we have a y. It's still the same thing, right? But if you have a function, if our original function that we're trying to take an inverse of, if it ever decreases, or if it ever goes up and then down, or down and then up, right? So essentially, if it increases, if it ever decreases at any point, or if it's decreasing and it ever increases at any point, now all of a sudden, if you do your horizontal line test, you have more than one point. So it no longer has an inverse that's a function. Does that make sense?
Yeah.
Okay. So I will do a problem. Which problem do you want me to do?
I think we can maybe just start with. Can we just start with number 3?
Number 3. Okay. So the function looks like. That's bad. Hold on. Okay. And we want to go from 0 to 1. Wait, what did the bounds even? It doesn't show where 1 is and 2 is, right? Or am I mistaken?
Yeah, I already see it. Does anyone else know?
He said that 2 is like near the end, and then 1 is before it starts going down.
Okay, yeah. So if I was making this problem, I'd assume 2 is over here and 1 is over here, right? And so
Yeah.
from this range, you can see that it's always increasing. Sure, it's concave down, but it's always increasing, right? Just in this range.
Yeah. So it is a function. So it's monotonic.
Yeah, monotonic. So A would be I'll just put check. And then B is from 0 to 2. So it's from here to here, right? And so we can do our horizontal line test. Okay, yeah, that definitely has one more x for every y once we find the inverse. Or we can do or we can just see, okay, it's decreasing, right? And so if he were to give you a function and ask if it was monotonic like he does in the later problems, you would just take the derivative and then make a y prime line and see if it ever changes, right? So do you want to do one of those, or do you think you're good?
Yeah, can we do one of those?
Okay, which one do you want to do?
5.
Okay, 5. We can do one of the other ones too if you need it after, but let's just do 5 for now.
Sure.
Okay, 5 2x squared, whoops, minus x plus 1, and x is all real numbers. I wonder why he puts that here. Could be because I guess he's just putting bounds on them. Yeah, never mind. Okay. Okay, so y prime is equal to 4x minus 1, right? And we can think about this in 2 ways. One, this is our y prime in 2D space, right? This is positive, so our y prime is increasing, and this is negative. Our y prime is, so our function is increasing when it's in the blue, and it's decreasing when it's in the red. Does that make sense? Because this is our y prime line.
Yeah.
Right, so that's one way you can think about it, where, okay, it's above and below the axis, so it is not monotonic. Another way you could do it is just find critical numbers, right? And so if you find critical numbers and then it ever switches from positive to negative or negative to positive across those critical numbers, then it is not monotonic. So like equal to 0, x is equal to 1/4, that's a critical number, right? So if we draw a y prime line, 1/4, as x goes to infinity, it's positive, negative. So it's switched, right? And you can see that visually over here as well. Does that make sense? Versus if this was like positive to positive, sure, it goes to 0, right? But that is only for a split second, right? So there's still only one y for every x. It does look like, hey, if I do the horizontal line test, isn't there a few of them? But no, it's just because I'm bad at drawing and I have a flat line there. In reality, there's only one, right? If I were to zoom in, it would look like.
Yeah, makes sense.
Yeah. So that's pretty much it. I mean, it's, yeah. Do you need me to do the other ones, or?
No, I think I'm okay. So basically, just like see if you take the derivative to basically look at like the slope, if it's constant or not.
If it's the same sign the whole way.
The same sign, right?
Yeah.
Okay.
Yeah. And then for tables, did he guys show you how to integrate with tables? Because I never really did that,
No.
and he never really showed it to us.
No, he didn't teach us either.
Yeah, I would just, there's a shortcut people do for parts where you like create a table. I don't get how it works, so it's like the diamond method when you're factoring, in my opinion. I don't get how it works that much, so I just don't do it. It's not that much faster anyways from what I can see, so yeah. Okay, any more questions, or?
Wait, so if the derivative is even, then it just wouldn't be a monotonic function, right?
If the derivative is even, well, I mean, that's a pretty good theory question, but wouldn't you say this is even? Oh, yeah, you would. Yeah, you're right. Yeah, never mind. I was about to say, oh, it can be negative. But yeah, as long as it stays on the same side. Oh, wait. But what about this? What about... That's even, right?
Yeah,
But it
but
goes...
doesn't that also fail the horizontal line test?
Oh, is this Are we talking about this as y prime or just y?
Oh, y prime.
So if this is y prime, then it goes from positive to negative, right? So it's not always increasing or always decreasing. So it's not monotonic, right?
Yeah, okay.
Does that make sense? You were saying
Yeah.
something about the horizontal line test, and I would do that. That would only apply to our y. So if we were to if we were to do this as our y, it would probably look something. If this was centered at the origin, which is what I'm gonna do, it would be like x cubed over 3. So it would be that, right?
Right.
Oh wait, but that is.
Wait, I have a question. So
Oh wait,
when
no,
we
there's
take
a
the derivative, only if it's a linear line, it would be monotonic, right?
only if we take the derivative.
And
Well,
it's fine.
okay. Let me first of all ignore that drawing I made, because that would only work if this was this, right? And then boom, it's monotonic. So ignore that, right? But like, yeah, so we're on the same page that this is not monotonic, correct? We're on the same page for that. Or do I need to elaborate that one as well?
Yeah, I think we are.
Okay, we're good. Okay, so I'm going to explain. So you were asking about a line, right? Well, what if I make a line, if our y prime line looks like that, and keep in mind that this is y prime. That's a line. It's going from it's both in the positive and negative. It is, so that means our y is increasing and decreasing. So that is not monotonic, even though it's a line. Now our y prime is monotonic. This is monotonic. Because if we take the derivative of this, it's always increasing. Or we can look at it visually, right? Look, it's always increasing. But our y is not monotonic. Oops. Yeah. Does that make sense? Is that I can go into further detail.
Wait, can you
That makes
elaborate on
sense.
that?
Okay. What questions do you have about it?
Okay, so if it's a y, if this was a y line, then it's not monotonic because
So let me redraw it. So you're saying if this was a y line, right?
yeah.
That was y. Why would that not be monotonic?
Would it be monotonic or it wouldn't?
Well, there's a few ways to think about it being monotonic. One, does it pass the horizontal line test? Does it only pass through the function once for every horizontal line I draw? Yes, right? So yeah, so that's one way we can think about it. Another way we can think about it is, oh, that's a line. So that's like y is equal to x minus 2. We take the derivative, y is equal to a constant. Let me put a c over there, right? Actually, let me just make this super general. Cx minus a. Y is equal to c. C never changes. C is always positive or negative or 0. But 0, actually, that's a good question, actually. Another thing, is that monotonic?
No.
No, because yeah, that is not monotonic, right? Because that would be basically the same as 4 plus 0x, and if we found the inverse, we would swap x and y, so x is equal to 4, and then that is not a function. So yeah, so that is not monotonic because the horizontal line that we pass through it passes through all the points, so it doesn't pass the horizontal line. So that was just something I wanted to clear up. So as long as c is not 0, which means it's a line in the traditional sense, right? What this is, right? As long as c is not 0, this is monotonic, right? Because there's never going to be any critical numbers. C is never equal to 0. I just said as long as c is not 0. So does that make sense? So it's either positive or negative the whole way through.
Okay, that makes sense.
Okay. Now on the other hand, if this was our y prime line, first of all, let me center this at the origin just so it's a little easier on me. What does our y look like? quadratic, right? And that does not pass the horizontal line test. So that's one way we know it's not monotonic. Also, if we look at it, right, there's two ways we can visually represent the y prime line. One, like this. Two, we can just think of it like this, right? And in this line, it's negative and then positive. So if this was our y prime line, our function would not be monotonic, right? Because it goes from decreasing to increasing, or it flip-flops, right? So does that make sense?
No,
Yes.
okay, that makes more sense.
Okay, any questions on that? Cool. Okay, so are there any other questions on anything you guys have done so far? Or
So by definition, it just means like, is its inverse also a function?
yeah, that's all. And
Okay.
and if the inverse exists, it has to always be increasing or always be decreasing.
Right. Okay.
Because if it flips, it then you get two x values for every y value, right? If it goes from increasing to decreasing, right, in our y and x, now there's two x values that satisfy the same y value. And then when we switch it, it's going to become that there's two x values, or there's two y values for every x value once we flip it, right? Does that make sense, or did I just complicate it further?
No, that makes sense.
Okay, cool.
So would a cubic function be monotonic? It wouldn't, right? Alright.
As an original function or as a y prime?
As a y. An
As a
original
y.
function. Yeah.
If it's our original function, well, does that pass the horizontal line test?
Yeah.
So it is monotonic, right?
Okay, yeah.
Right, because
Alright.
if you think about it, our y prime now becomes a quadratic. And
Yeah.
hold on, wait. Yeah, our y prime now becomes a quadratic, so it stays in either the positive or the negative realm only, right? So it's monotonic. Make sense?
Okay.
So yeah, it is important to think about, is the function I'm talking about the y prime or the y?
Right.
Okay, any other questions?
I have two questions from trig substitution.
Okay.
I'll send a picture in the chat.
Is there any other questions that I can answer quickly? Like about monotonic functions or anything like that? Or are we good on this? Okay. Alright, cool. So I think, yeah, these are pretty easy, so.
So for number 10 and 12, so for number 12, do we use a triangle in the first place, or?
Let me find. You put it in homework help. Okay. Number 12. Yeah. Okay. So the way I would do number 12 is I would complete the square, and so we get. Let me complete the square. X squared plus 6x plus 9 minus 1, right? And then we get x plus 3 squared minus 1, right? And then I can make a triangle out of that. So this x plus 3 is 1. Or, oops, that's not a good triangle. X plus 3, 1, square root, x plus 3. Do you see where it goes from there?
Yeah, that makes sense. I think I got it from now. I just need to set up.
Yeah, so that's how I would do that.
Got it. And how
Yeah,
do we approach number 10?
Number 10. That's just another triangle. It's probably written weirdly, so it's just 1 plus x squared plus 49.
Oh, okay. So that's just like x on one side and a 7 on the other.
Yeah, x and 7, so then this is x squared plus 49.
Okay, that makes sense. Thank you.
Okay, so that's that. Is there anything else? I think you guys have gotten the hang of integrals by now. There's not much more. There's a few other stuff you learn in BC, but other than that, yeah. Any other questions or? Okay. I mean, if there's no more questions, I guess we could end. I'll see what I can figure out about hyperbolic functions and type what I can. All right. Thank you for coming. I'll probably have another tutoring session next week if you guys have more stuff. Otherwise, we don't need one. So,
Thank you. Bye.
all right.